All right. Next, we have another method also extended from second order linear ODE. Yeah. So let's look at the details. All right. C.3, method of variation of parameters. Yeah. This vector version. Yeah. This time, let us solve the same question, but we use a different method. Okay? Yeah. All right. Because we want to focus on the procedure part, yeah, the standard steps in the solution. Yeah. All right. So the same example, so we're familiar with that. So for the homogeneous solution part, we already have the homogeneous. Okay? Yeah. So here we can save some time for the homogeneous part. YH, yeah, let's write it out. Yeah. So but this time, let us write in this form. Yeah. Yeah. Why are we writing this form? Yeah. Because if you still remember the main idea of this method of variation of parameter. Yeah. So we did that before. We derived the formula for the second order linear ODE. Yeah. We did that. So here we just follow the same path, deriving that formula. Yeah. But here we do not do the derivation. Yeah. So here we just write the formula directly. Yeah. But we need to do some preparation. In order to write the formula, here we do preparation. So what kind of preparation we are doing here? So we write the general homogeneous solution, YH. So here, first we do preparation on the homogeneous general solution part first. When we do the preparation, we write in this form. So what is this form like? All right, so two E functions using two eigenvalues. Yeah. Then the coefficient part, vector coefficient. First, second, two vector coefficient. Yeah. And we know they are constant coefficient. Yeah. For the homogeneous part here, we use the constant coefficient. All right. Now, when we change from homogeneous to non-homogeneous, yeah, we need to make that change. Yeah. So definitely, we cannot use the same solution as in the homogeneous version. We have to change significantly. In order to go from homogeneous solution to non-homogeneous solution, we have to change the nature, basic property, fundamental property, significantly. Okay? Then you can get something different, yeah, significantly different. Yeah. Here we do that change. So what kind of change we do? All right. We change on the coefficient part. Okay? Coefficient part. Yeah. Coefficient part for the homogeneous version, we use constant coefficients. Constant. No variable, no t variable involved. Constant coefficients. But when we move to non-homogeneous, we use variable coefficient. Variable coefficient. That's the significant change. All right? Yeah. So if you recall our old derivation procedure, yeah, we did that. We use the UV functions. UV functions. Okay? So here, yeah. All right. So here, yeah. So that's the, yeah. All right. Yeah. So here we write it in a matrix expression. Matrix expression here, you can see C1, C2 constant, right? C1, C2 constant. Now, can we use two functions, non-constant functions with t involved? That's the significant change, right? That's the significant change. Yeah. All right. Yeah. All right, so here, if we use, because this is the fundamental matrix, capital Y fundamental matrix. All right. So we write it as capital Y times C vector, constant C vector. The change we want to make is on the C constant vector. We change from constant C vector to a variable function vector. U or V, a function vector. Okay? All right. Yeah. So here, Y, capital Y is a function of t, but capital C is not a function of t. Yeah. All right. Now we make the change. Yp equals U of t matrix times U vector of t. Yeah. So U vector should contain variable t. So it's a function vector. Okay. U1, U2, they're both functions of t. That's the change we make. Okay? Yeah. Because this change is significant. Okay? Significant. So then we have a chance to get Yp solution. Yp. Because Yp is for non-homogeneous. Yeah. Containing the G part. If we do not do this big change, we have no chance to get a solution containing the G part. Okay? So that's the reason. Yeah. But U functions, U1, U2, two functions can be determined by the formula. All right? Yeah. All right, so let's take the derivative. The first way we take Yp derivative directly from the assumption structure here. Okay? Product of two one matrix, one vector. Okay? Product of matrix and a vector. So we have the product rule, derivative product rule. Yeah. Yeah. Here you can see, that's the derivative product rule. Okay? Yeah. So here we apply the product rule for the derivative. Yeah. All right. So y prime times u plus y times u prime. Yeah. That's first way. Second way, yp prime, you just go back to the original equation. A times yp equals yp equals capital Y times u, then plus g. Okay? Yeah. These two expressions should be the same. Yeah. So we have this equation. All right. All right. So now we need to work on this new equation. Yeah. Here you have matrices, you have vectors, you have derivatives. It looks a little complicated, right? Yeah. It looks pretty complicated. Yeah. In order to simplify it, here we want to simplify it. Otherwise, this equation is too hard to solve. Yeah. We want to solve this equation for u. Now, if we do not do simplification, it is too hard to solve. So we will do some significant simplification. Yeah. All right. Now we need to go back to the definition of y. You need to you need to be familiar with the structure of y. Then you can simplify it. Okay? So how to simplify that y and the y prime? Yeah. So let's back to the homogeneous solution. Okay. Let's go back to, when we derive the homogeneous solution, what equations those y should satisfy. Yeah, we go back to that point. Yeah. So we write our fundamental matrix y, capital Y, in these two y vector solutions. Y sup 1, y sup 2. Two vector solutions. Yeah. Because y1, y2, they are two solutions of the homogeneous system. So if we plug in to the homogeneous system, they should satisfy the homogeneous system. Yeah? So that's the, the basic meaning. Yeah. All right. First, let's plug in y sup 1 vector in that homogeneous system, right? So this is the original homogeneous system. Yeah. And we plug in y sup 1 solution. Yeah, it's a solution, so it must be correct. Okay, that's the first one. Second one, for y sup 2, we can also plug into the original homogeneous solution. It should also be correct. Yeah. All right. After we have these two equations, now we combine them. Yeah, we can combine them. All right. Yeah. Okay. Yeah. All right. So the property here. Yeah. When we combine, we use a simple property. So what's that? Right? So here I just want, this is very simple. A matrix A multiply matrix X. But this X, we use two column vectors. X sup 1 column vector, X sup 2 column vector. It equals the matrix, also matrix, two vectors. The first vector is A times X sup 1. Second vector is A times X sup 2. Yeah, so that's simple. A very simple property. Yeah. Just based on the matrix product. How do you do matrix product? So this is, same way you do matrix product. Yeah. All right. Now, with this property, now let's go back to, put these two solutions together. All right. Now, first, A times Y equals, based on this property, here we use Y vector. Y sup 1, Y sup 2, we replace X vector by Y vector. Okay? So you have A times equals A. Yeah. All right. Yeah. Yeah, because A times Y, you write Y in its two vectors. Then you apply this property. You get A times Y sup 1, A times Y sup 2. Yeah, these two vectors. That's AY. Okay? That's AY. Yeah. All right. Then, all right, I hope you can follow. Yeah. All right. Then, we look at the derivative part. So this is the AY. Okay, AY. We have this expression. Okay? Yeah. Then we look at the derivative part. So what's the derivative part? Right. All right. Derivative of Y matrix related to derivative of these two Y vectors. All right. Yeah. So here, let me just copy the, useful equations we need from the, previous slide. Okay. Yeah. Otherwise, how to keep track of them? Yeah. Basically, I just copied the, a few related formulas here. Yeah. So we can continue. Yeah. All right. Next, we want to see the derivative part. Yeah. So I also copied these two. Derivative equations. Yeah. All right. So below our new derivation, below that dashed line, our new derivation. Okay. All right. Then y prime. What's the y prime? Yeah. Y equals y1 vector, y2 vector. So y prime equals prime of y1 vector and the prime of y2 vector. Okay? Yeah. Yeah. Straightforward prime. Yeah. That's the prime. Okay? y1 vector and y2 vector. Prime. Okay. All right. All right. So now, what's the y1 prime, y2 prime? Okay? y1 prime, y2 prime by these two equations, a times y1, y sup 1, a times y sup 2. Yeah? So directed from the above two equations. Yeah? All right? And then this one, yeah, look at these two expressions. This expression just the ay. Okay? Yeah, so we get y prime equals ay. That's the intermediate result we want to have. Yeah. In order to do simplification, we want to get this intermediate result. This intermediate result. Yeah. All right. Yeah. Okay. Then, so here, let me write in a clean way. Okay. This is our intermediate result we need to use to simplify this equation we want to simplify. Okay. Yeah. All right. So now, yeah, here, the next step, I want to connect you to, so next step, so how to derive it, how to do this deduction. Here, if you go back to this equation, okay, go back to this equation, you compare these two terms. Y prime part, ay part the same, then you multiply the same u. Can you see these two terms the same? Right? This is the critical step. Can you see these two terms the same? Yeah. Because you have this, y prime equals ay, okay? Y prime. So we spend so much time, okay? We get a y prime equals ay. Now we apply this property, yeah. So cancel out, okay? All right. So these two terms the same. We cancel out from that equation. After cancellation, we have this y prime times u. Oh, sorry, yeah. Because this one we get a y. Yeah, we just multiply u both sides. Yeah. This side, so we can do the cancellation. Okay? After cancellation, yeah, we just write the remaining two terms. After cancellation, y times u prime equals g. Yeah. Now it is much simplified. Okay? Yeah. Before simplification, it's too hard to solve, right? Too complicated. But after simplification, much easier to solve. Yeah. And we can see we are very close to the solution. Yeah. Very close to the solution, final solution. Okay? All right. Yeah. Question. Can we find u from y and g? Y is known, right? Yeah. After you solve the homogeneous equation, y is known. G given in the original question, y matrix known, G vector known. Can you find the U vector that satisfies this equation? Right? Not too hard, right? Yeah? All right. Yeah. And we know Y is invertible. Now you understand the invertibility property is important for Y, right? Yeah, Y is invertible, so you can multiply Y inverse matrix. Y inverse matrix. Yeah. All right. Yeah. All right. So fundamental matrix Y is invertible. Now, here. Yeah. Yeah. here I review. All right, so we spent quite some time understand. At the beginning, think about it, at the beginning of this class, I spent almost half an hour to explain that whole slide. One of the main point is Y is invertible. Yeah. So the n column vectors of the fundamental matrix Y are linearly independent. Okay, the Wronskian, non-zero, linearly independent. If an n by n matrix is not invertible, then its n column vectors are linearly dependent. Yeah. Dependent. Okay, that relationship. Yeah. All right. Then from the determinant, yeah, we also see the invertibility of Y from its determinant. Determinant of Y not equal to 0. Yeah. Determinant is the Wronskian. Remember? Yeah. This determinant, that's our definition of the Wronskian. W of capital Y. Okay? Determinant, that's the Wronskian. Wronskian not equal to 0. Okay? All right. Now, after we know Y is invertible, we can calculate Y inverse. If we apply Y inverse, we can find a U prime vector equals Y inverse times G vector. Yeah. Y is known. Y inverse can be calculated. Yeah. So can be calculated. Okay. Yeah. Inverse. So there is, some standard process to calculate matrix inverse. Yeah. And G multiplication, so we can find U vector. To find U, we take integral of this known vector. Okay? Y inverse times G, it is a known vector. We take integration on the known vector. So we get the U vector. Okay? U vector, if U vector is known, YP is known, right? Yeah. Look at our YP assumption. If U vector is calculated, YP is known. Yeah. Then the whole problem solved. The whole problem solved. Okay? Yeah. So here you can see, yeah, we can extend this method of variation parameters from the scalar version to vector version. Here, our solution, we use the vector version solution. Okay. All right. Yeah. Now, let's go back to our current question. Yeah. Before, we did the general derivation. Yeah. Because we can apply all these formulas on all other questions. Yeah. Yeah. Questions satisfying the pattern we have here. Yeah. So Y matrix is here. How to find Y inverse? How to find Y inverse? Okay? How to calculate Y inverse? Remember, I gave you 2 by 2 matrix inverse formula last time. Yeah, right. 1 over determinant. Then the matrix, you swap, negative. Yeah. So that formula. Yeah. So I copy that formula again. Yeah. Yeah. Here, let's calculate the matrix inverse. Yeah. So let me copy. Yeah. So here, Y is this matrix. Yeah. Formula of 2 by 2 matrix inverse. Yeah. A inverse equals 1 over determinant of A times 2 by 2 matrix. But the matrix entries, diagonal entries, you just swap. Okay? 2 diagonal entries, you swap. Then non-diagonal entries, you do not swap, but you multiply by -1. You change the sign. Yeah. Non-diagonal entries, you change the sign. Okay? So that's the matrix inverse formula. Now we are ready to calculate our final solution. First, we calculate determinant of Y. Determinant of Y, you do, cross product, then you take subtraction, So that is the first cross product, second cross product, but you take a subtraction, you get a negative 2 times e to the negative 60. That's the determinant. All right. Then y inverse 1 over that determinant, then y matrix, we swap the diagonal entries, then non-diagonal entries, we change the sign. Yeah. That's simple. Okay? Yeah. So we do not need to do very complicated calculation. Yeah. We just apply formula. Okay? 2 by 2, we have this simple formula. But 3 by 3, you know, it's too hard. Yeah. 3 by 3, although there is a formula, but much harder than this one. Yeah. All right. Now we are ready to calculate u prime. Yeah. Y inverse times g vector. Yeah. Just do the, you know, straightforward. Yeah. So here I simplify 1/2. We multiply to the vector. We can do cancellation, right? So 1/2, because the scalar we can multiply to, you know, any, you know, matrix vector. So here we multiply to the vector part. So -3 cancellation 2 factor, then 2 also cancel out. Yeah. So we do this multiplication. Okay. All right. This multiplication, this vector, there is a e2 common factor we can factor out. Yeah. Right? E to the negative 2t common factor we can factor out of the vector. Okay? Out from the vector. Yeah. This e2 scalar we can multiply through inside the matrix part. Yeah. Yeah. Multiply through into the matrix. A scalar multiply a matrix, so each entry we do multiplication. All right? That is, you know, 1, 1, e to the 2t minus e to the 2t. Yeah. Yeah. So before we do matrix product, we do some simplification first. Yeah. Then the product is much easier. Yeah. The product. That's the u prime, right? We need to take integral u prime on this vector, u prime vector. Integration. Yeah. So the next step, u equals integral of this vector. Yeah. All right. So each function we take the integral, but we need to add a constant vector. Yeah, because that indefinite integral, there is a constant term there. So here we use that b vector as the constant term. All right. So that's the u. We have that u. Yeah. All right. Yeah. So b vector we use b1, b2. Yeah. Yeah. So we can write the u vector with these two constants. Yeah. All right. Yeah. Next, we want to write the final solution. Yeah. Final solution. Yeah. All right. Yeah. So yp equals y times u. This is the u. Okay. All right. So y times u. Okay. Y times that u. All right. All right. Then you do the multiplication. You get this expression. Y times u. Yeah. 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 All right. So hope it's not too complicated for you. Yeah. All right. All right. Yeah. So next, our final slide, we want to write the final solution, adding up YH part, YP part, and at the same time, we want to do some simplification. Yeah. in our final expression, we want to simplify it a little bit. Yeah. The last step. All right. So the last step, YH, we have the YH expression, like this vector, C1, C2. YP, this expression, we have B1, B2. Okay? Yeah. Yeah. So all these C1, C2, B1, B2, so you can use, arbitrary constant. Arbitrary constant. Yeah. All right. Then, after we add up these two vectors, yeah, now that's the final expression. But final expression, yeah, it's correct, yeah, but it may not be the simplest form. Yeah. After we get this form, we want to try our best to make it a little simpler. A little simpler. Okay? Yeah? Yeah, all right. Yeah. How to make it a little simpler? Yeah, here. Yeah. Because when we look at C1, C2, B1, B2, they are arbitrary parameters we can choose. People can choose arbitrary. And they are independent. When you choose these C1, C2, B1, B2 parameters, they are independent. Yeah, so you have a lot of freedom to choose these four parameters. Okay? All right. So now I want to simplify in this way. Look at C1 plus B1 for the top function. We also have the same C1 plus B1 on the top function. They are the same. Okay? Since C1 plus B1 appear both top and bottom in the same form, can we use one symbol to represent the sum of these two numbers? Yes. Good. You get it. Yes. You get it. Yeah. Because in this way, we eliminate one. Right? Yeah. So this one, that one. Let us just use C1. Okay? We don't need a B1. Let us just use C1 to represent it. Right? Yeah? Yeah? All right. Then, let's try to do this similar thing for the second expression. Yeah? Because everybody hates the complexity. Right? Everybody likes the simplicity. Yeah? Hates the complexity. Yeah? All right. Let's do a little more simplification on the second part. Okay? But second part, C2 plus B2 and is minus C2 plus B2, they are different. Yeah, so here you cannot use one. This time you cannot, right? Right. So this time you have to do something extra. Do something extra in order to make it simple. All right. Can you write this one as minus C2 plus B2 plus 2B2? Can you do this change? C2, because you want to match the same expression, so you associate a B2 plus B2 with C2 in the parentheses. But when you minus B2, you need to add one B2. So B2 add B2, you have 2B2. How about that? How about that?
I would not have known to do that.
Yeah.
Okay.
Yeah. I mean, yeah. Try to, make up. Okay. Yeah. So this term a little short. So C2 is a little short. You compare with the C2 plus B2. There is a B quantity short. Okay. So you add it. You make it up. Okay. Make it up. Yeah. Right. But you make it up here. You need to, make it balanced. Yeah. Make it balanced.
Yeah, it's still the same thing, but I
Yeah, same thing. Yeah, but same thing. The importance of that is because after that, you can you have the same expression, you can use C2. Here, you can use C2. Yeah, you can use C2 because the same. Right? Same, use C2. Yeah, right? C2. But here, there is a 2b left. 2b left. Yeah, so you need one 2b, but b is arbitrary parameter, right? 2b also arbitrary. 2 is gone, okay? Because you don't need that 2, right?
Because it can be part of B2.
Yeah, part of B2.
Okay.
Because, yeah, right. So, yeah, try to get used to this kind of simplification. Although you don't have to, yeah. So if you do not do simplification, you get full credit, yeah. But it is highly recommended, yeah, because, yeah, do the best, do the best you can.
Aren't they all arbitrary? So couldn't you just combine them without having that, taking out the negative sign and just
Combine?
Can't you, like, before you factor out the negative sign, can't you just combine them in the first place?
How do you combine? How do you? Yeah.
Since they're both arbitrary constants, can't you just say negative C2 plus B2 is already C2?
You need to consider. If you make assumption one place, you have to consider, if your change affects some other places. That's important. Correlation. You need to consider the correlation. Okay? Yeah. Because here we make the same form, then we take care of the correlation, right? We change one place, the other place also changed. So we take care of the correlation. If you without do this thing, you just apply, new variable here, there, this place should be different. Okay? This place should be different. All right. Now I write the, final form. Now you can see we get this expression. Yeah. The final form, you have C1, C2, then you have a B. All right? Yeah. You have a B. Yeah. 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 I hope, you can, this part. Yeah. All right? Yeah. This part as negative C2 plus B2 plus 2B2. Okay? Yeah. So that's the, you can see our best effort to do the simplification. The best effort to do the simplification. Yeah? All right? Yeah? Yeah? But it's optional. Yeah, definitely it's optional for you. Yeah. But if you can do things like this, that's good, Yeah. Yeah. So now you can see, people play math like this, So you control the symbol notations, because we want the symbol notation serve for us, okay? Yeah. So when you have freedom, you have a lot of room to do the manipulation like this. Arbitrary parameter, yeah, arbitrary. We have freedom to choose. Now, we do not change anything, right? So here you can see, fundamentally, we don't change anything. No fundamental change. Yeah. No. But simpler, yeah, simpler. Yeah.
I guess I'm confused because I don't understand. I thought with like arbitrary constants, you could just like say, even just with the negative C2, you could just like eliminate the negative because it's an arbitrary constant.
Yes, yeah, okay, yeah, right. Yeah, you use C2 is okay, but you have to, if you make this C2, you have to make that a negative C2. Okay? You cannot change one place. You need to change everywhere it is affected. All right? When you make one change, you need to change globally. Okay? You cannot change something locally. Yeah? When you change notation, because other places using this same notation, you need to change accordingly. Otherwise not consistent, right? Here we want a consistency.
Because then the C2 is not consistent. To
Right.
the other row.
Right. Not consistent. Yeah. Yeah, make sure all your change, if it's consistent, it's legal. If it's not consistent, you break the system. Okay? If you make any change that is not consistent, you break the system.
Okay, so just to be clear with my understanding, so if it was just one row,
Mhm.
you could just make it C2.
Yes.
But since
Yeah.
there's two rows that have to stay consistent with the same content,
Right.
you have to keep them. Okay.
Yes. Yeah.
Thank you.
The consistency. Yeah. You know. Yeah. Yeah. Good. Yeah. So we finish this part C because only 5 minutes left. So let's do not start a new part. Yeah. Yeah, only 5 minutes. Yeah. We do not.
I can do it. I can do this.
Yeah. All right. Yeah.